Measurements and calculations. All right, I discussed in chapter 1 an introduction, what chemistry is and why chemistry, and kind of give you a flavor. Now we're going to get serious about some of the things we do in chemistry, and many of the things require some type of measurement. And then we take those measurements, and they're usually what we call raw data. And you've got to do some calculations with them for you to make sense of them. So that's where we're headed with chapter 2, and then we'll talk about matter in chapter 3. All right. Oh, by the way, does anybody have any trouble with getting into Cengage? Got Cengage? Okay, Cengage. Good. Okay. Let's see. I know one of the students, I think Emily Murphy, can't be here with us live or Zoom. She's working. I'm not sure about Laurie. Or maybe I've got it backwards. But the format, the modality of the course allows for that. So if you do your assignments on time, then I count you present. Or if you show up, of course, that's even better. All right. What do we get with a measurement? If you just say I would say, let's see, end of February, I'm going to say I'm 72. You can just naturally think I'm 72 years old. But what if I really meant to say I'm 72 inches tall? Not quite. I'm about an inch shorter than that. That's 6 feet. It's important to have the unit along with the number. Otherwise, the numbers don't mean anything. Now, there are some pure numbers that do mean something if you know where they came from. But for the most part, when you make a measurement, you've got to have a unit of measure. And if I have something that's, say, this long, and I put a ruler up to it, it looks like it's about 12 inches. Right? 12 inches. But it's also 1 foot. Now, did the length change? No. Well, the numbers, the description of it changed, but the length actually didn't change. That's a physical quantity. And our measurement is what changed. But these two are equal. And we're going to take advantage of that in a few minutes. So a measurement always has it's also known as a quantitative observation. Quantitative. Just when you see quantitative, think numbers. Okay. So what's the other possibility? Qualitative. It's just a descriptive term, like sky is blue. We don't make any measurements about it. We just observe that it's a certain color. Or Jim is bigger than Joe. We don't say how much bigger. We don't even say what their heights are. Those are qualitative observations. Okay. But these two parts are always necessary, the number and the unit of measure. Let's see, sometimes we call, okay, my brain a minute to catch up. Sometimes we call this part the scalar, this part the dimension. Probably number and unit are easier to remember. All right. Some of the numbers, the measurements that we make are extremely large or extremely small. They can be either. This particular example here, 93 million. You know where they got that one? It doesn't have any units with it, so, we can make something up. They probably got it from the distance in miles from average distance from the Earth to the sun, 93 million miles. But if we just focus on the numbers, 93 million can be written with all those zeros, or it can be written as a product of two numbers. And 9.3 times 10 million is 93 million. So we're going to reduce that 10 million to a power of 10. And all you have to do is count the number of zeros. So it's 9.3 times 10 to the 7th. The 9.3 is called the coefficient. I know in math, coefficient can mean lots of different things, but in the sciences, that's what coefficients mean. And then we have the power of 10. So they're equivalent, but this is a more compact way of notation for the number. All right. What happens if your coefficient is exactly 10? If it's exactly 10, then you have to move that power into this number. So then it would be 1 times 10 to the 8th. There's a difference between, you might see this, exponential versus scientific notation. Exponential notation just means you can have any combination of coefficient and exponent and give you exponential notation. We could write 930 times 10 to the 5th. That would be exponential notation. Scientific notation is a subset of that and requires that this coefficient be between 1 and 10. If it gets to 10, then you have to go to the next exponent. But that's the difference between exponential and scientific. And sometimes you'll read, authors will equate them, but they're not really the same. All right. So it's important to, when you're converting back and forth between scientific notation and standard notation, it's important to know which way to go. I always look at the exponent and say, right, if I take that exponent and put it over here to make that number, that standard notation, then the number has to get bigger because that's a power of 7. Or if it was a negative, then that number would have to get smaller. And that tells you which way the decimal moves. You move the decimal point this way for the positive and this way for the negative. Okay. It's like we're storing up information in this one right here. We stored up 10 million. Yeah. For that number. And that's the beauty of the decimal system, right? It's just factors of 10, right? Rather than some odd, like, I don't know, the English system where you have 2 cups in a pint and 2 pints in a quart and 4 quarts in a gallon. And, you have to memorize all those. And the English system of monetary system used to be that bad. I think they've squared it away with decimal equivalents now. Okay. So there we've moved the decimal to the left so we can store up positive powers of 10 in the exponent. This one, on the other hand, we would have to move the decimal to the right and we store up negative values of 10. So we move the decimal to the right 2 places. That means 10 to the minus 2. Okay. All righty. Okay. Scientific notation for this number. $7,882. If we're going to, if there's not an explicit decimal, of course, we assume that there's a decimal right here. That shows you the ones, tens, hundreds, thousands. Then we can move it to the left. 1, 2, 3. There. And put that motion over here in the power of 10. Scientific notation. So the answer should be C in this case. Okay, how about this one? How many zeros? 1, 2, 3, 4 after the decimal. And then 496. Okay, in this case, we're storing up negative powers of 10. 1, 2, 3, 4, 5. We have to move it over here to that. So 4.96 times 10 to the minus 5. We did it that way. And by the way, when you write a number that's got zeros to the left and there's a decimal in there, don't leave that zero off. A lot of my students come out of public schools and the teachers there allow you to do that. And that's wrong. Okay. That's what I call an orphan decimal. It needs both parents. Okay, so there's our answer for that one. We've already covered that. The number and the unit. Okay. If you're making a measurement, say with a meter stick, you can have units of, say, centimeters or millimeters. Or if you're using a balance in the lab, it'll read off in grams. But sometimes you can get units of measure that are compound. And that second one, 6.63 times 10 to the minus 34 joules seconds, is an example of that. Those types of measurements, in fact, that's a constant that we use in a formula later, but this is more important for calculations than it is for measurements. Sometimes you can get these compound values out of an instrument if the instrument's like a black box. It's doing stuff on the inside you don't know about. You're making measurements with the instrument and it spits out an answer with these compound units. But what it's done is it's done some calculations for you internally. I don't like those types of instruments because, you know, they garbage in, garbage out. They might tell you something that's not true. Kind of like using AI now, right? They say AI can just make stuff up. They've got a name for it. Actually, it comes from psychology. The AI is psychotic. But the important thing to remember is when you got, say, a number like this, let's do this. Let's make it like that, like this, like that. You're dividing grams by cubic centimeters. Well, if these don't cancel, right, they're different units. You have to do the same thing to the units that you do to the numbers. So 1/2 would be 0.5, wouldn't it? And your units would be grams per cubic centimeter. If you're going to divide the number, you have to divide the units too. That's a basic fact. But if you have a calculation where they're times each other, then it would be like this one, joules dot seconds. Dot means times. Okay. So when scientists are going to make measurements, it used to be many years ago, alchemists in particular would invent their own units of measure so that they could develop their recipes for looking for turning lead into gold or finding the elixir of life, that type of stuff. But even they eventually settled upon standard units so that they could talk to other alchemists. And we carried that through into the modern era by standardizing fundamental units. This is the international system. It's SI units because it's based upon the French, right? So they do everything backwards. So these are fundamental units. They're the ones that are established by convention and agreed upon by all scientists. And we've delegated that authority to a committee and usually several subcommittees that specialize in these different types of measurements. And the first one is mass. We settled on the standard mass is a kilogram. And to establish that one, we took the gram from alchemist days, which would be pretty tiny. So we multiplied kilo, which means 1,000. We multiplied kilo times that to give us our standard. Because if you try to standardize a small mass, it's very difficult to do first. And second, if you even touch it, you've affected it percentage-wise. You've introduced error. So they created a 1 kilogram mass made out of platinum and iridium alloy, which is very inert, stable. But that's not good enough. You take that kilogram mass and they put it in a bell jar and fill it with argon. And then they put that in another bell jar and fill that with argon to stabilize it over time. And they keep it at constant temperature in this cave in France. We haven't devised any other way to standardize that mass yet. You have to use the standard kilogram. The meter, the distance, the length fundamental unit has been modified. Originally, it was a platinum iridium bar of a certain shape. It was like this, like that, like that, like that, like that, and like this. It's a certain shape so that this there. That's a cross section. The bar goes this way so that it wouldn't warp. And it was a standard meter length. Now, where did that meter come from? Well, they used the Earth, North Pole, equator. The distance between those 2 points passing through Greenwich, England, where the observatory is located. They took that distance and then they subdivided it to make a length that was manageable. So that's where the standard meter came from. And they have this bar in the same cave in its own bell jars. But now we are able to standardize our meter using laser light. And a certain laser wavelength, a certain number of wavelengths of this laser light will give you a meter. So you're not dependent on the bar anymore. All you need is lots of money to buy the instrument. So it's usually restricted to large corporations or governments to own this instrument. But it will standardize the meter for you without having to go to that cave. The time fundamental unit, the second, is inherited from astronomy. And all we did was we took what was considered to be an average value that was brought forward from the Dark Ages and just standardized it. And now we have a standard second that can be accurate to within like dozens of decimal points using an atomic clock. We use the radioactive decay of an isotope, and that measures the so many cycles of that measures our second. We need that high accuracy now more than ever because of our satellite systems, right? Especially GPS. If the satellite that's sending you a signal, and you need at least 3 of them in order to establish a position on the surface of the Earth, 6 is better. But if that satellite, when it's sending you the signal, doesn't know where it is, then it can't tell you where you are. So it needs to know exactly its time signature relative to some standard. And we've also observed with those satellites Einstein's relativity. As you increase your speed, other things go out of whack. So you have to have an accurate time signature in order to establish both your position and your speed. Temperature, standard is Kelvin. And don't freak, the size degree, say on a thermometer like this, the size degree here, this Kelvin, 1 Kelvin, is the same size as Celsius. Okay. It's just that Celsius has a 0 point here and it has negative values here. It can go negative or positive from that 0. Kelvin starts from 0, absolute 0. So it starts from here, and all the Kelvin numbers, degrees, well, we don't say degrees, we say all the values of Kelvin are positive. We need those for calculations later. It'll become obvious, especially when we get to the gas laws. That you need, so it's convenient to make measurements in Celsius, but for doing calculations, very often you need Kelvin. Not always, but often. The electric current is the ampere. In this course, we're probably not going to deal with that. That's actually a compound measurement. It's so much charge in coulombs that passes a point in a conductor every second. So if you have a breaker box in your house that's rated for 200, 300, 400 amps, that's what they're meaning. That's what they need. It has that capacity. Now, we are going to be interested in the mole. The mole, actually, the whole word is that, and the abbreviation is this. Go figure that one. The mole is an amount of substance in terms of counting. So we count numbers of things. And if we have 6.022 times 10 to the 23rd things, we have a mole. So for our purposes, it'll be a mole of atoms, a mole of molecules, a mole of ions, that type of thing. But it's still just a number. However, it is based upon the natural world phenomena. It is calculated from that. And the significance of the mole become much more apparent once we get into the periodic table. Okay, has everybody started memorizing their symbols yet? Okay, flashcards are good. All right. The sooner you learn those, the better, because we're going to be using them over and over and over again. It's like trying to speak a foreign language when you don't know the alphabet. Prefixes are used to change the size of units because the fundamental unit may be too big or it may be too small. Like when we, let's see, what would be a good example? How long does it take to drive from Beckley to Atlanta, where I have people? Roughly 8 hours, with stops. So I didn't use seconds, did I? I used hours. So how many seconds are in an hour? 60 seconds in a minute and 60 minutes in an hour. 3,600 seconds equals 1 hour. If I had said, what's 8 times 3,600? That's a pretty big number. It takes me that many seconds to get to Atlanta. No, I use an hour. It's a bigger unit. So we use, this is an example of changing units, but in the decimal system, it's even more convenient because all we need is a prefix to the fundamental unit and we have a new unit of measure. Now, one of those fundamental units we've already discussed already has a prefix, right, for a good reason. That kilo means 1,000 times. So it's 1,000 times a gram is 1 kilogram. But suppose you want a gram. Well, you've got a gram and while this is the fundamental unit, this is called the base unit. Sometimes the fundamental units are base units. Sometimes they're not. But if we want to change a fundamental unit into some other unit, we need these prefixes. I've already expressed kilo. The small k is 1,000 times the value. So it takes 1,000 grams to make a kilogram. Notice that when we say, let's get too busy. Let me make some room here. When we say 1 kilogram equals 1,000 grams. Notice what happens to the units when to the numbers when the unit size changes. When the unit size gets smaller, the number gets bigger. They're always that way. They're inverted. So if we go this way, the unit size gets bigger, so the number gets smaller. That's one way that you can use to check yourself for calculation purposes, right? When I was in the first lecture, you have these steps that you can go through, right? What's the question? What information do I need? What plan of action to solve the problem? And then the last step is, does it make sense? If you had, if you expected the number to be bigger, but it's way small, then you know you went the wrong direction. Okay, kilo, mega is 1,000,000. And you can go smaller values too. Deci before it would be like a decimeter. Right? 1 decimeter is actually 1/10 of a meter. Another trick you can use if you're going back and forwards is to say, all right, this deci means 0.1 times. So there it is, decimeter. A centimeter is 100th of 0.01 milli, right? We've all heard of millimeters. Micrometers, right? Have you had a biology course? Have you used a microscope? Yeah. So you know that if you're standardizing your oculars, you may have a slide with a very finely etched thing on it, and the distance between each one of those might be a millimeter, it might be a micrometer, and in your microscope, you can standardize the ocular lines. One of the oculars might have etched in it some lines that you can use to measure the size of cells. Well, you can't put the slide with the lines etched on it and the slide with your cells on it at the same time. So you have to standardize your eyepiece, right? In micrometers usually. Nanometers, 1/1000th of a meter. Right? If you wear sports clothes these days for exercise, very often they'll have nanometer-sized fibers in them, or they'll have deposited in them nanometer-sized compounds of some kind to help them wick away water, or to stop you from stinking, you know, whatever the case may be, or whatever the business can make money on. Okay, so we talked about this one. The meter is the SI fundamental unit. In this case, it's also the base unit. So 1 kilometer is 1,000 meters. So how far is it from here to Charleston? Well, it depends on where you go. Let's make it easy on ourselves. Let's say you're on this side of the city, maybe it's 50 miles. So 50 miles is how many kilometers? Well, the kilometer is 1,000 meters. But the kilometer is actually smaller than a mile. So in order to get to miles, we need to multiply this times 1.6. So that means we would have to divide this one by 1.6. No, excuse me. We have to multiply. excuse me. I'm confusing you, I know. 1.6 times miles equals kilometers, because as the unit gets smaller, the number has to get bigger. So 1.6 times 50 would be proper. We're going to go into this in a more logical fashion in a few minutes when we talk about dimensional analysis or unit conversions. So don't let that throw you yet. Let's see. All right, we've talked about those already. Volume is another issue, because volume is in 3 dimensions, and we don't have a fundamental unit for volume, because volume is height times width times length. Right? So we use the fundamental unit to derive a unit for volume. Okay. In this case, 1 cubic meter is an acceptable unit for volume. It's that blue cube is 1 meter on every side. So that's 1 cubic meter. But that's not very convenient. All right, so we take 1/10 of each of those sides. So we have a decimeter cubed. That's that little red square in the lower left-hand corner. That cubic decimeter is given the unit of measure liters. Right? So 1 liter equals 1 cubic decimeter. And liter is more commonly used everywhere else in the world except US. Right? We still use gallons, but everywhere else you use liters. Nice thing about liters is liter is let's see, 3.8 gallons. So it's less than a gallon. Well, 3.8 liters in a gallon. So a liter is a lot smaller. It's a little bigger than a quart. And the nice thing about that for governments and businesses is you can charge your fuel by the liter. So it used to be a very small amount, like maybe 25 or 30 cents a liter. With a smaller unit of measure, you can increase the cost to something that's similar to what we're paying for a gallon now. Although in Europe, it's probably like 15 or equivalent of $15 or $20 a gallon. Anyway, the liter is the fundamental unit for most volume measurements. We still use cubic meters for very large volumes, or cubic centimeters for solids, and cubic and for liters or milliliters, thousandths of a liter, for liquids. It's just by convention. Then if we take that decimeter and take one side and take 1/10 of a side, now we get a decimeter on one side, and 1/10 of that is a centimeter, right? Because a decimeter is 10 to the minus 10th meters, and this is a decimeter, and a centimeter is 10 to the minus 3. Oh, excuse me, 10 to the minus 1. And 10 to the minus 2. There we go. 1/10 of a meter is a decimeter. And a centimeter is 10 to the minus 2 meters, 100. So the difference between these two is only 1/10. So if we take 1/10 of a decimeter, we get a centimeter. And if we cube the centimeter, we get a unit of measure that's equivalent to 1,000th of a liter, a milliliter. So a cubic centimeter is equal to 1 milliliter. Right? Anybody in the health professions? Right. So do you still have anything laying around that's in cc's? Okay. That's cubic centimeter. That's what that means. Now they're transitioning over to milliliters. Right? Because our printing is, we're able to print things better now. Easier, cheaper. They went to cc's, because it's easier to write cc's than it is to put cubic centimeters on the package. So, but if you ever see something measured in terms of cubic centimeters, you can just automatically convert that to milliliters. You don't even have to use any conversion factors because they're equivalent. Okay. It says the SI unit is a cubic meter, but that's only because it's based upon the fundamental meter as the length. Solid volumes, I mentioned that earlier, and that's an important factor. Remember, 1 milliliter is 1 cubic centimeter. All right, how about mass? All right, we have a balance in the lab that will measure the mass. Actually, we have several balances, but we have one we call an analytical balance that will measure the mass of an object or substance down to an accuracy of 4 decimal places or 1/10 of a milligram. Okay. This particular balance, it looks like it has 4 decimal places. It's kind of hard to see, but 89.2863. So 4 decimal places is its accuracy. Now we used to measure the mass of things by comparing them with standard masses. So when I started in chemistry, we had these big green machines made by Mettler. And they had inside, you could take the lid off and look inside. They had these standard masses attached to things that would allow you on the outside to spin dials and move them around. And it would compare the mass of whatever you set on the balance plate to those masses in that box. Now the balances are they have stress cells underneath the plates. They're called piezoelectric. In other words, they change the amount of the current that they will allow to flow through them based upon the pressure against them. And they're very accurate, very stable. In fact, you don't have to take as much care with them as we did with those old balances. Right? The old balances we had, if you wanted to move one, you had to go through an elaborate procedure of locking everything down. So it wouldn't, because the balance itself, someplace in that balance was a knife edge. And it was usually a crystal that was shaped so that it had like just a couple of 3 atoms on that edge. And it could be easily damaged. Okay, so the SI unit is the kilogram, but notice that balance measures in grams. So let's take that example, 89.2863. 89.2863 grams. If we wanted to express that as kilograms, that means that this unit would get bigger, so that number has to get smaller. By how much? By 3 decimal places. Excuse me. 0.892863. That would be the equivalent. Now, if we want to convert to a different system, you need a conversion factor. In this case, we've established by comparison of many measurements that 1 kilogram mass will weigh 2.2046 pounds. Now we're, let's see. Yeah, I'm trying to think. The first chapter, we covered the difference between mass. Did we cover the difference between mass and weight? Or I'm getting that confused with my other class. We haven't done that yet. Okay, there is a difference between mass and weight. Let me see if I've got a slide. I don't want to steal my own thunder. Maybe that's coming. We'll talk about matter. Oh, well, I'll just tell you anyway, since we're going to get there eventually. Mass is a measure of substance. A measurement of mass does not change anywhere in the universe, as long as you're not traveling close to the speed of light or close to a black hole. Otherwise, mass is constant. But weight is a measure of force. And it's a force that is either the result of a mass in a gravitational field, like on the surface of the Earth, or the surface of the Moon, or is experiencing acceleration, which simulates the weight. Okay, that's why you can go to these fairs. Have you ever been to the fair where they have the spinning thing with a carpet on the walls? Right. And you're standing there and they get you spinning and then the floor drops out, but you don't go anywhere because there's a simulated centrifugal force holding you against the wall. Right. So that's like simulated gravity, but it's still a force. It's not a mass. It's the result of mass under certain conditions. So I said all that to say this, that when we say 1 kilogram equals 2.2046 pounds, that's only valid on the surface of the Earth, because pounds is force and kilograms is mass. As long as you understand that, then we can make those conversions. We can go the other direction. 1 pound is 454 grams. Those are conversion factors, and we're going to learn how to use those in a little bit. Okay. Choose a statement that contains improper uses of commonly used units. Doesn't make sense. Okay. A gallon of milk is equal to about 4 liters of milk. Does everybody in here read labels when they go to the grocery store? No? I'm still the only one that does that. If you read the label on a gallon of milk, it'll say 1 gallon, 3.8 liters. So that's true. It's about 4 liters. 200-pound man has a mass of 90 kilograms. It's about 2.2 pounds for each kilogram. So that means cut that in a half, a little less than half, 200. Yeah, 90 kilograms is fair. What I'm doing in my head is estimating. It doesn't have to be down to the decimal point, right? Just to get me in the ballpark to see if it makes sense. A basketball player has a height of 7 meters. He might be 7 feet, but 7 meters are like 22 or 23 feet tall. That one doesn't make any sense. A nickel is 6.5 centimeters thick. How much is a centimeter? Develop an intuition for sizes too. We know an inch is about like that, right? A centimeter, 2.54 centimeters in an inch. So a centimeter is about like that. Right? 6.5 centimeter thick nickel? I don't think so. So those last two don't make any sense. All right, this is an extremely important concept. Uncertainty. We've got all these standardized measures that scientists agree upon. But if you get two people, even if they're using exactly the same meter stick to measure the length of something like a sheet of paper or, I don't know, the length of a cow, they're going to come out with two different values because every measurement has uncertainty. We can never know exactly what the measurement is. The best way to get something that's really close to the measurement is to measure it several times and average them. Especially if you've got several people working on the same problem. Okay, so that's the first rule. Every measurement has uncertainty. So if we recognize that fact, we just have to deal with it. How are we going to deal with uncertainty? One way is that all scientists recognize that when you present a value, a measurement, a number, keep it simple. If I put that number into a report and another scientist looks at it, he or she knows that I am saying these numbers here are certain. In other words, I'm going to guarantee that those numbers are immutable. They don't change. The last one, that's the uncertain number. So it could be 3, it could be 2, it could be 5, it could be 6. It's probably going to be close to 4, but it may not be exactly 4. That's the uncertain number. The last digit is the uncertain one. Okay. Now, how does that relate to actual measurements? Well, your measuring device usually has some way to, has calibrated values on it. In this case, we've got a ruler, but it could be anything, measured volumes, measured masses. It has some way to calibrate and has, uh, for our purposes here, it has these lines on it. What do those lines mean? Well, if you look at the bottom one so that we can expand it, that nail is somewhere between 2 and 3 centimeters. And then there are subdivisions in there between the 2 and 3. There are 10 of them. So we're talking about 1/10 of a centimeter or a millimeter. Okay. So if we're still in centimeters, then we have to say it's between 2 and 3. We know that, between 2 and 3 centimeters. It was between 2 and 3, and then we look down closer, and it's close to 2.8. Okay. Then what are we going? Oh, we're going between 0.8 and 0.9. Okay, I have to back up and re-argue. It's between 2.8 and 2.9. Okay, well, it falls exactly on that 5, which is between these two, which means 2.85. Okay, now I think this slide is probably okay. This actually illustrates the problem with presenting the value as 2.85, because now we assume that the last digit is uncertain, and it's not. So I should have done this, because 5 has a value there that we can read. Okay, but if we present it that way, whoever sees that number is going to think that 5 is uncertain. Okay. Excuse me. I've used a term that I haven't defined yet. I used accuracy. In the sciences, accuracy has a very specific meaning. It describes how close, either in a quantitative or qualitative way, how close is your measurement to the true value? Or if you don't know the true value, the accepted value. Okay. If it's very close to the accepted value, we say it's an accurate measurement. Precision, on the other hand, doesn't say anything about how close the measurement is to the true value. It just says, what's the distribution? How close are multiple measurements to each other? So if you make 2, 3, 4 measurements, are they grouped close to one another? So on our example earlier, if we had that somebody else measure that in centimeters, they might come up with something like, if they positioned the nail wrong, they might come up with something like this. Or if somebody else did it, they might come up with something like this. This is an example of high precision, because they're very close to one another. Now, when you're actually doing the measurement, and we're talking about accuracy, how close is your measurement to the accepted value? There are 2 factors that come into play. One is your instrument. How accurate is your instrument? And usually, the more accurate the instrument, the more it costs. And then the other factor is the technician who's using the instrument. How well are they trained? How conscientious are they at operating the instrument properly? Here are our examples. There's one where, is anybody a shooter in here? No, okay. If we had a couple of guys, one would probably be a shooter. But before deer season, you want to be sure your rifle is on target. And you set the range at whatever you think you're going to be at, 150, 200, 300 yards. And then you take usually three or more shots at the target with your scope. And if it comes out like this, then you have low precision. In other words, you've probably got a barrel that's worn out, right? The grooves are just worn out and your bullet's not coming out of the barrel straight. But if we average those together, notice we get a value that's right on the bullseye. So this is an example of low precision, high accuracy. Okay. The next one, say, you've got your rifle and you take those 4 shots and they give you a better grouping. So you got better precision in this case, but it's not accurate. Right? And that's okay, because now all you have to do is dope your scope and move that group up onto the bullseye and take 4 more shots and see if you're on target. And if you are, you might have something like this. Okay? High accuracy, high precision. Now, the other possibility is scattered all over the place and the average is nowhere near the bullseye, right? That's not accurate and it's not precise. Oops. There we go. All right. Now that we've got a definition of accuracy, precision, and we know that all our measurements have some built-in error, we've got to learn how to deal with it. Well, the first way, of course, was certain versus uncertain numbers. But if you're going to do calculations, you need to know how to track that uncertainty through the calculation so that you can be honest with the end product. And we're going to start with that, counting significant figures. Have you ever had math class introduced significant figures? No? Okay. This will be new. Okay, when you're looking at a number, a measurement, a number, and it's got several digits in it, and you look at them and you see, all right, that number has all non-zero integers, right? Every one of those is significant. Like this one. There are 4 significant figures in that number. Okay. Then if you got, did I go too quick? Okay. Then if you have a 0, it can be in different places in the number. So those zeros may be significant or they may not. Right? The first one is leading zeros, or that zeros precede a non-zero digit, but there are no, like this, 0.057, like that. These leading zeros are not significant. So this number has 2 significant figures. That's always the case. Leading zeros are not significant. Okay. Then we could move a 0 into the number itself. 507. There we go. How about that one? All we did was just swap the 5 and the 0. Now this is called a captive 0. Captive zeros between 2 non-zeros are significant always. They have to be significant, otherwise we don't have the same number. Like this one. That one has 4 significant figures. Now, it doesn't have to have a decimal. We could have just as easily written this one, and it would have 3 significant figures. And then the other type of zero is to the right, trailing zeros. Trailing zeros are conditional. It all depends. If this number, say, let me add a zero on the end of that number. 5070, 5070. It's understood to be a decimal here because that's ones, tens, hundreds, thousands. But it's not an explicit zero. Decimal, excuse me, an explicit decimal. That means this trailing zero is not significant. So that's 3 significant figures. If we made a measurement and we intended it to be significant, then all you have to do is put a decimal there. And that makes that last zero significant. If there's a decimal, an explicit decimal, anywhere in the numbering, then the trailing zeros are significant. So for this one, if we had like that, 1, 2, 3, 4, 5 significant figures in that one, because there is an explicit decimal in that number. Okay. All right. 4 there, only 2 there for 150. And the last class of number these are exact numbers. In other words, we are by convention saying that these numbers, exact numbers, have infinite significant figures. And we say that so that when we do calculations, exact numbers do not limit the significant figures in the outcome. And there are 2 classes, usually counting numbers. I think sometimes they use pencils, like 9 pencils. 9 pencils have infinite significant figures. Because you can't, well, I guess you could, but for our argument's sake, we don't have half pencils. If you cut it in half, now you got 2 pencils, but they're still counting. And the other are equalities, conversion factors. If we say 1 inch equals 2.54 centimeters, then both of those numbers have infinite significant figures. And I'm going to show you a better explanation for that in a few minutes. That equality, that equivalence, allows us to create a conversion factor. Because now, if we know that 1 inch equals 2.54 centimeters, if we have a number that's measured in centimeters, we can use that to convert it to inches, just like we did with 1 foot and 12 inches earlier. But those are infinite significant figures. All conversion factors are like that. Okay. This is like out of place. Exponential notation. Well, it should be scientific notation. Oh, I see. We're talking about it in terms of significant figures. Excuse me. All right. Let's take this one the way it was, like that. How would we write that as scientific notation? Well, let's see. We move 1, 2, 3. So we have 10 to the third, and the decimal's right here, 5.07. Right? That 0 is not significant, so we don't put it in the coefficient. If we wanted it to be in the coefficient, we would have to do that. Now it's significant. And the coefficient retains the number of significant figures from our standard notation. Okay. Something like this, we would say 1, 2, 1, 2, 10 to the minus 2. And that would be 5.70. Let's do it like this. Just 5.7. Because these zeros are not significant. It actually wouldn't make any sense to keep those zeros out here. That would look kind of wonky. Okay. All right, we can, if we do it right, the scientific notation will give us the number of significant figures. And then the zeros that are not significant are thrown out, like 93 million. That's why we wrote 93 million as 9.3 times 10 to the 7th. All those zeros to the right were not significant because there was no decimal point. Okay, we're going to use rounding. 5 or above is round up, less than 5 is round down. But it's important to remember that if we want to round, say, 507, let's put this like that. If we are restricted, say this is an answer to a calculation, and we know that we can only have 3 significant figures in the answer. Then we have to round to 1, 2, 3, to that position right there. That means that to determine what this one should be, we look immediately to the right. It doesn't matter what else is out here, just this one. That's less than 5. So it would become 5070. And it would still only have 3 significant figures. Okay. Yeah. We don't make the mistake of saying, I don't know, 1, 5, 8, 9. We don't make the mistake of saying, we need to round this to 2 significant figures. Right? So what's this one going to be? Well, we don't go down here and say, round that one to 9, round this one to 5, round this one to 4, and then leave that one. Now, just by chance, we came out with the same value that we would have if we'd done it right. You just look to the one immediately to the right. I picked a bad example. I should have picked one where it would round up until the one that we were supposed to look at is over 5, and that would have given us the wrong answer. And that's one of the reasons that when you're doing a calculation, if there's only multiplying and dividing, I better save that comment. Hold on a second, because I haven't given you the rules for calculations yet. All right, we know that one. Okay. Rounding, this rule is the one I was going to give you, but it's not going to make any sense until I give you the calculation rules for significant figures. Just so keep that one in the back of your mind, and I'll give it to you again. Okay, mathematical operations. We have 2 types of mathematical operations that require different rules. The easiest one is multiply, divide. And you've got a series of calculations that require only multiply, divide. Then all you have to do is carry the calculation through to the end, and then look at the numbers that were used to multiply and divide. Find the one with the smallest significant figures, smallest number of significant figures, that is applied to your answer. So in this case, we only had 2 numbers. The smallest one had 2 significant figures. So your calculator might tell you 7.381, but you know you can only have 2 significant figures. See, calculators are kind of dumb like that. They don't do significant figures. So we round it to 7.4 because we know we can only have 2 significant figures. And that works for any series of calculations that are multiply, divide. Now, if you have an add, subtract, my lines are off there. I have to fix that animation. Add, subtract. In order to do add, subtract, we line up the decimal, whether it's explicit or understood. Let's see, they've got an example for us. It'd be easier to do it this way. There we go. Come on. 23.445. We line up the decimal with 7.83. Then you just add them together, whatever the operation says. If it's subtract, of course you subtract. So 5, 7, 12, carry the 1, 11, 3. That's what we get. But in add subtract, you're limited to the one that's furthest to the left in significant figures. That means that 7.83 limits the answer to 1, 2, 3, 4 significant figures. And we have to round this one up because that one is 5. 31.28 is our answer. Notice with add and subtract, this number has 5 significant figures. This number has 3 significant figures, and your answer has 4. With add subtract, you cannot tell just by looking at the significant figures of your operators what the answer significant figures are going to be. You have to do the calculation in order to determine. Unlike multiply divide, you know that the smallest number of significant figures determines the answer. But with add subtract, you got to do the calculation. Okay. Now, sometimes, let me get rid of my animations. We'll go to that in a second. Sometimes you have calculations that are compound. In other words, some they have add, subtract, and multiply, divide embedded in them. In that case, you have to follow rules of calculation, right? Parentheses, exponent, multiply, divide, add, subtract, in that order. Unless if they're given parentheses throughout, then you're good, you're safe. So whatever happens in the parentheses, you do that first, unless the parentheses is like x times y over z. That's multiply, multiply, divide. So you can just do that whole thing and use the 1, right? But if there's an operation in here like that, you would do that one first, then divide it in there. You would find out what the significant figure for this one is and apply the rule. Then apply the divide rule. Okay. So it all depends on that. Most of the time in our calculations, we're going to be using multiply divide because most of the calculations we're going to do are unit conversions or solving formulas. Most of them are going to be simple multiply divide type formulas. I can think of one that would have an add subtract in it, like when you're converting Celsius degrees. That gives you an add subtract rule. We'll cover that. You'll see that again in just a minute. All right. This just emphasizes the fact that if you're using more than one instrument in the process of producing a result, the accuracy of your results, the outcome, is going to be determined by the least accurate instrument. That would be the one on the left, because its subdivisions are 2/10, whereas the graduated cylinder on the right is 2/100 subdivisions. That's just to demonstrate that the accuracy, actually, I guess we could include precision there too. Actually, the precision requires introducing the technician as well. Okay, problem solving by dimensional analysis. Dimensional analysis is just a fancy pair of words. That means unit conversion. And in dimensional analysis, we want to pay attention not just to the number, but to the units of measure, the dimensions. There are a number of problem solutions that you can do in chemistry, actually in the sciences, if you understand the concept of dimensional analysis. You can follow the dimensions through the calculation and end up where you want to be. Not always, but very often. We convert from one unit to another. And the reason we can do that is two things. One is if we're making a measurement, the physical property doesn't change. It's only our units that change. And in order to make that change of units, you need an equivalence. Something's equal to something else. All right. Those are just step-by-step procedures. It'd probably make more sense if I just do a problem and show you how it's done. All right. This example. A golfer putted a golf ball 6.8 feet across the green. If that was me, I'd miss it. How many inches does this represent? Okay, 6.8 feet. Right? And we want to end up with inches. Okay, how do we get there? Well, we know there's a relationship between feet and inches. Right? We know that 1 foot equals 12 inches. Those are exact numbers. Let's see, we need to multiply this by something that gives us inches. Well, we know in math that you can multiply anything by 1 is allowable, right? But that doesn't get us where we need to go. Look at this. Suppose I divide this equation. I can divide that equation through by 1 foot, both sides, right? If you do the same thing to both sides of an equation, you haven't changed it, right? It's still equivalent. That's a mathematical axiom. Notice what 1 foot divided by 1 foot is. It's just 1 with no units. Okay. So if we put 1 in here, that won't help us. But if we put the equivalent of 1, 12 inches divided by 1 foot, that looks like it might get us where we want to go. So notice that this number, if the number is sitting there by itself and there's no line, a divisor line, it's always in the numerator. So that's the numerator. It's like that. So that means numerator, denominator, the units cancel. And now we're left with numbers to multiply. So 6.8 times 12 is what? There it is. I got it animated. Come on. 82. I should have been able to do that one in my head, but I just didn't feel like it. So these are infinite significant figures. So this is the one that determines the outcome. 2 significant figures, 2 significant figures. 82 inches. Now, the distance to the hole didn't change, but the units of measure did. So the units of measure went from feet to a smaller unit. That means the number went from 6.8 to a bigger number. Okay, that makes sense. All right. Oh, I've only got till 11, right? Okay. All right, this happens to me all the time. I got to get through chapter 2, but you may have someplace else to go, right? You may have another class. You may have to get to work. You may have to pick up a kid or whatever, family issues. If we run out of time, since there's nobody in this class after me, I just keep going and recording. And then I post it on the Brightspace and you can finish it up later. Unless you have time and you want to sit here, that's fine with me. Let's see, I was just looking. No, nobody else. I guess the other 2 students are going to be web-based. So that being said, we'll continue on. If we want to go from 4.5 pounds to grams, notice we're not just going size of units difference, we're changing systems. So 4.5 pounds, we want to convert to grams. This is where we are, that's where we want to go. Sometimes it helps to go backwards. If we know that pounds is equivalent to a certain number of kilograms, and it's given there in the parentheses, then we're going to have kilograms down here going to grams. Right? So that means we need to convert pounds to kilograms first, and then kilograms to grams. So this is what's called a chained conversion. Dimensional analysis tells us that this pounds needs to be in the conversion factor in the denominator so that we can cancel it. So the pounds is 2.2046 is 1 kilogram. That cancels the pounds. Now we need to cancel the kilograms. It needs to be in the denominator, and 1,000 grams here. Okay, so now we've done, that's what I call the thinking part. We've done all the thinking. Now we just crunch numbers. So when you go into your calculator, I hope you're all proficient with your calculator. All you need to do is say 4.5 times 1,000 divided by 2.2046. There's your answer. Now, most of my students, I haven't found one student yet that has my type of calculator. This is called reverse Polish notation. So the way it works is you say 1, enter, 1 plus. So whatever's in that register 1 first, I put the second one in, I say, what do I do with it in relation to the register that I just put in? And that's why the plus comes after. But algebraic calculators say 1 plus 1, and you have to push the equal sign. So learning how to operate your calculator is essential. That makes sense so far? Okay. So the answer is given here in scientific notation, 2.04 times 10 to the third. And this is an exact number, that's an exact number. So we have 3 significant figures. 2.04 is 3 significant figures times 10 to the third. And if we wrote that out in standard notation, 1, 2, 3, 2, 0, 4, 0, 3, like that. Okay, it's going to take practice, right? If you haven't done this a lot, that's why in that review document, I give you lots of these examples. You can drill them. All right, I'm not going to spend time on this one. This is another example, a real world example of chain conversion. You're going to make a trip from New York to Los Angeles, although right now I wouldn't do that. For me, let's say I'm going from Beckley to Atlanta, where I have kin, right? I want to know how much money do I need to take or have in my account so that I can buy enough gas to get down there and back and drive around while I'm there. Well, you need to know some things. You need to know how far is it. You need to know what's the gas mileage of your vehicle on average. And you need to know what gas is going to cost per gallon. So you have 3 conversion factors. Okay, well, this is New York to Los Angeles, 2,500 miles, 25 miles a gallon, and $3.25 a gallon. So there's your chain conversion. And that says I need $325 just to get there. So $650 to get back. And then you want to pad it a little bit for driving around and variations in price per gallon. So I would say $650, at least $700, maybe $750, to be sure that you don't get stuck in the middle of nowhere. Okay, here's our temperature system. There are basically three temperature systems that are used in the sciences. Fahrenheit is predominantly used in the United States, and our weather system, our weathermen, meteorologists describe temperature in terms of Fahrenheit. So we have an intuition about what that is. Right outside now, it might be 15 degrees or 17 degrees Fahrenheit. We know what that feels like. But we can convert that to Celsius, which is the system that's used everywhere else in the world. And then if you're a scientist, you want to convert to Kelvin. Well, these came in chronological order. Fahrenheit came first. He was a German working with biological systems. And all you need is a reliable device that changes with temperature. And what was settled upon, I can't remember who actually invented the first thermometer, but the bulb contains mercury. And then you have a very small capillary. It goes right up through the center. And mercury, being a heavy liquid, a dense liquid, a metal, will expand and contract with temperature. And if you make the capillary small enough, the volume changes the same, no matter what the size of the capillary. But if you make the capillary small enough, then you can get it to move a certain distance for each degree in your system. So for Fahrenheit, he established 0 degrees. Let's see. He established 0 degrees as the coldest temperature he can get, which was salt and ice, like these ice cream freezer. Okay. And the high temperature, the 100, was what he considered to be the average temperature of warm-blooded creatures. We now know ours is 98.6. Cats and dogs are like 102 to 104, right in there somewhere. So he took 100 there, and then he just subdivided it. So now he has 100 degree units between 0 and 100. Celsius came along later. Celsius was more of a chemist or a physicist, and he wanted something that was easily standardized. So his thermometer said that 0 degrees is the freezing point of pure water, which would be in this neighborhood right here. And then 100 degrees is the boiling point of pure water at 1 atmosphere pressure. And it would be up in this neighborhood. And then he subdivided his, and that gave him his Celsius degree. Kelvin came along about the time that thermodynamics was in its infancy and being developed. And he recognized the need for a system with no negative numbers in it. So he used, and I'll talk about this again later when we get to gases. He used gas properties to say, all right, at what point will an ideal gas, at what temperature will an ideal gas have no volume? And that's his 0 point. So his thermometer would be different, and his 0 would be way down here. And then and it would be the same size degrees as Celsius, only the 0 point is moved from here to here. So Kelvin is going to be a higher number. At 0 Celsius, Kelvin is 273.5. Okay. We generally, when we make calculations, 273 is good enough. All right. Oh, there are thermometers. Okay. Now, when you're measuring the temperature of some object, just because you use a different thermometer doesn't mean that the object's temperature changed. It just means you use a different unit of measure. So we got the same physical property, but a different unit of measure. Now we can convert Celsius and Fahrenheit with this formula. Degrees Fahrenheit equals 9/5 degrees C plus 32. Some of your books will say 1.8. That's fine. It's exactly the same number. This is the way I learned it. So this 9/5 accounts for the difference between the size unit between Fahrenheit and Celsius. And this 32 adjusts the 0 point because the 0 point is going to be different. Right? 32 degrees Fahrenheit is the freezing point of water, which is the 0 point for Celsius. That's why 32 here. And then when you convert Kelvin, Kelvin is going to be degrees C plus 273. So if you got to convert Fahrenheit to Kelvin, you got to go this one first and then that one. I suppose you could combine them algebraically, but I'm not going to do that. Has everybody had, oh no, this is a 100. You just have basic math, right? Anybody had algebra before? No, okay, that's fine. You doing algebra now? Okay. That's the link to a website that describes this conversion, if you're interested in more detail. All right, I'm going to have to skip this. This is the case where you convert Fahrenheit to Celsius and then Celsius to Kelvin. And there's the animation for it. So 102 degrees for a dog is 39 degrees C. What's Celsius body temperature for humans? It's 98.6, right? Fahrenheit. Okay. It's exactly 37 degrees Celsius. That's nominal normal body temperature for humans. So dogs are a little warmer, cats too. I think most mammals are warmer. Birds are a lot warmer. Oh, here's an interesting question. Since we have different size units, if you draw them on the same graph, at some point those lines are going to meet. And that will tell us that at some temperature, Celsius is equal to Fahrenheit, some value. So in order to solve that, all we have to do is take this and substitute X, because if that's equal to that, they might as well be equal to that same number. And then just solve for X. Right? Solve your equation in one unknown. And if we do that, let's see, I think I've got it here. Right, go X, X, X. Let's see, there we go. Solve for X is minus 40. So minus 40 degrees Celsius equals minus 40 degrees Fahrenheit. That is very cold. I know from personal experience. I used to work at a hotel and restaurant supply house while I was going to school for my bachelor's, and once a month we would inventory all the product in the place, all the dry goods, everything in the cooler, all the meat hanging on hooks, all the storage freezer, which is at minus 20, and then the blast freezer, which is minus 40 degrees. And since I was low man on the totem pole, I was a part-time student, I got to do the blast freezer. So they would feed us a high calorie breakfast. They just go back in the back and pull down bacon and sausage and biscuits and whip us up gravy and, and get the calories up way up there. And then we'd all go to work early in the morning. And I go in the blast freezer with my big gauntlet gloves and my floor length quilted coat and cap. And I had this huge pencil that I could hold with big gloves. And I'd start taking inventory. I'd be in there about 10 to 15 minutes max. I have to come out and cool off. I mean, warm up in the cooler. So those were the days. I was getting paid, so I did what I was told. Okay. Density is one of those compound units. density is a measure. Let's see. Okay, I don't have a slide on it in there. I'm going to give it to you on the board. There, the various measurements that you can make can be classified in two categories. One is an extensive property, and the other is an intensive property. The extensive property varies depending on how much substance you have. So mass would be a good example. The more stuff you have, the greater its mass. Intensive property is something that doesn't change no matter how much you have. And density is a perfect example. Density equals mass divided by volume. So if you have a greater volume of gold, you're going to have more mass. But when you divide the two, you get the same density. Right? I like to use gold. So that's the basic difference between the two. Sometimes you'll see it like this. This is a extensive property as a capacity factor. And this is an intensity factor. I've seen it both ways. Your book probably uses the bottom one. So density is an intensive property. It doesn't change with amount of substance, either volume or mass, because when one changes, the other changes. One thing that can change density, though, is what? Well, it depends on the substance. The temperature, right? That can make the same mass expand to a higher volume if you increase the temperature. Or if you increase the temperature for a gas and you maintain the same pressure, then it has to expand. So temperature can change density. But once you've measured density at certain physical conditions, it doesn't change. And it's a formula. Density equals mass divided by volume, which means these are three variables. They can be different numbers. If you know two of them, you can solve for the third one, right? That's algebra, basically. So if we know the mass and the volume, we can calculate density. If we know the density and the volume, we can calculate the mass. Or if we know the mass and the density, we can calculate the volume. And the units of measure depend on whether it's a liquid or a solid. If it's a liquid, it's usually going to be grams per milliliter. If it's a solid, it's going to be grams per cubic centimeter. But the number is going to be the same, right? Because milliliters and cubic centimeters are equal. Now, if we're dealing with gases, it usually takes more gas to give you a measurable mass. So gases are going to usually be grams per cubic meter for their densities. Now, how do we measure? Well, if you need to measure the mass, you just use a balance, right? For our swimmer, you'd have to have a big balance or a doctor's scales. But how do you measure the volume of an irregular object, right? A regular object is easy. Like if you have a cube, it's just that times that times that. Or some other regular object. If you have a cylinder, it's like height times area. But if you have an irregular object, the best way is by displacement, right? You take our swimmer and you measure the volume before, and when she jumps in the water, the volume is going to go up. As long as she's completely submerged, then the volume will go up in equivalent to her volume. And now you have her volume and her mass, you can calculate her density. Well, her average density, because bones are more dense than skin. So if your object floats, how do you get it to sink? Say you have something that's less dense than water. How do you get it to sink in the water? You add weight to it. So I would say, if I had something I want to put in that tank, it has to be completely submerged in order to measure the volume. Right? If it's only partially submerged, you're only measuring the volume that's submerged. So if I had something I wanted to submerge, I'd like tie lead weight on the bottom of it, and then hold it up here until the lead weight was in the water. That's when I measure the volume. And then I turn it loose, and the rest of it will go under. That would give me the volume of the object, because you've already taken account into the volume for the volume of the weight by submerging it first. Okay. All right. I'm just going to let this animation go. 17.8 grams and a volume of 2.35 centimeters. Just do the math. And remember, the units have to be retained because they don't cancel. In this case, we know that we've got this volume of liquid. We have that density. By the way, if that liquid does not dissolve in water, will it float or sink in water? It'll float because it's less dense. Less dense objects float in more dense objects. So you can have, if you have a pool of mercury, you could take a rock, throw it in there, and it would float because the rock is probably less dense than mercury. I think most minerals are like 2.6 in the neighborhood grams per cubic centimeter. And mercury is like 13.5 grams per centimeter density. So that rock would float. But it would sink in water because water is 1 gram per milliliter. All right, in this case, we want to solve for mass. And we determine the mass of that object. Okay, what I'm trying to illustrate with this problem is that to determine the density in grams per cubic centimeter, you say, all right, the formula says we need grams here and cubic centimeters here. We've got grams, that's good. But we don't have cubic centimeters. We have 0.125 liters. 0.125 liters is how many cubic centimeters? Well, we know there's 1,000 milliliters in a liter, right? So if the unit gets smaller, the number has to get bigger by how much? 1,000. 1, 2, 5. 1, 2, 3. So 125 milliliters is also 125 cubic centimeters. So that's what you put in the volume. Got to pay attention to your units. That get you in trouble. Yes, just ask the engineers that sent that probe to Mars, right? They had several companies that were manufacturing pieces for it, and some of them were using English units and some of them were using metric units, and they calculated the intercept for the planet with one set of units, and it should have been the other set, and they lost the signal. They eventually figured, oh, it crashed. So a several $1 million project was ruined because they didn't pay attention to their units. All right, so there's our calculation of the cubic centimeters, and then put that in our formula, and there's the density. So the density is greater than 1, it'll sink in water. All right. For this problem, sometimes it helps to draw pictures. So in this problem, we have copper has a density of 8.96 grams per cubic centimeter. So I like to extract information. 96 grams per cubic centimeter. Extract information from word problems. One thing that you'll learn, if you haven't already learned it, word problems are designed to confuse. That's their primary purpose. They're designed to confuse, just to be sure that you know what you're doing. So that's why I extract information from word problems and put it in a form that I can recognize. 75 grams of copper is the mass. 0, yep, got an extra 0, grams. And we're going to drop that mass of copper in 50 milliliters of water, and we want to know what's the volume reading afterwards. So if I draw a graduated cylinder, sort of, and it's at 50 milliliters, let's say it's 100 milliliters graduated, so it'd be 50 milliliters here. And this is the amount of water that it has before we put the copper in. Okay? If after we put the copper in it, right, down here, what's it going to do? It's going to increase, right? So it's going to go up to something, I don't know, something up here. And the difference, this volume difference is the volume of that copper nugget. Okay? But the answer we want is this. What's the final volume? So we need to add 50 plus V. Okay? Our formula for density, if we solve for volume, is going to be mass divided by density. But that's just this V. That's not the answer to the problem. We're only partway there. So if we put the mass 75 divided by 8.96 grams per cubic centimeter, then we'll get a certain volume here. 75 divided by 8.96, right? And that's 3 significant figures. So I've got 109. Yeah. No, that's not right. That doesn't make sense. Let's try it again. This is better. 8.37. What's the units? Well, remember in math, this numerator grams is in the denominator, and that's the numerator. So these cancel. Well, what happens to the cubic centimeters? The denominator of the denominator is a numerator, which means this flips into the numerator. Okay? So that's the volume change. We would have to add, is that 50.0? Yeah, 50.0. So 50.07385. And we can only keep this much here, so it's 58.4 milliliters should be the final volume reading on the instrument. Go. And then there we go, 58.4 milliliters. Okay. This is a multi-step problem. So that's why drawing a picture helps. And yeah, I've given you in your review problems and in paper exams, I gave you lots of space to scribble. If you need to do some thinking with your pencil, you got lots of space on that paper to. And in fact, if you work a problem out on that paper right next to where you want the answer to go, and I see that you worked it out, and I see that you got you got the wrong answer, but you were on the right track. Well, if the questions are worth more than 1 point, you can get partial credit. You just made a math error, maybe. Okay, matter. What is matter? I can remember grade school definition for matter. Anything that occupies space and has mass. It's just that simple. We're concerned in this course only with 3 states of matter: solid, liquid, gas. Because the conditions under which we're investigating these various states are rather mild. You can go to extreme conditions and end up with all kinds of different states of matter. Probably the closest one to us is the sun, plasma, like ionized gas. That's a different form of matter, but we're not interested in that. Solid, liquid, and gas. Okay. What you'll notice, if you can look at matter on the atomic scale, you'll see that solids have a regular arrangement of atoms and or molecules. Did I describe difference between what a molecule was in the first one? Let me see. In case I have to talk about it again. No, I'm getting that confused in my other class. Okay. Atom, of course, is the smallest subdivision of an element that retains the properties of the element. Okay. And if you combine one or more atoms in bonded in such a way that they behave as a single unit, you get a molecule. So when you learn your symbols, you'll know that, say, hydrogen atom and a hydrogen atom bound together is an H2 molecule. Okay. You can also have molecules with different atoms, like water. So water would be like 2 hydrogens combined with 1 oxygen. And they're bound together so that they behave as a single unit. Okay. In our example here, we have solid. The solid is ice. And you notice there's an irregular arrangement of those water molecules in a cube of ice. That allows the solid to both retain its volume and its shape without any outside requirements. However, when we add enough heat, we break the bonds that are holding those water molecules together, and now they're able to slide past one another. We didn't get them so far apart that their volume changed, although in water it did change. I'll explain that in a minute. But what we've done is we've retained the volume of the solid, but now we have a liquid that must have a container to hold it. So it doesn't have a definite shape anymore. It acquires the shape of its container. If we add more heat in such a way that we can break any bonds holding those water molecules together in the liquid state, we get a gas or steam. And that's characteristic of gases is the molecules interact with one another very weakly. And in fact, if we treat them as ideal gases, they don't interact at all. They're very far apart and they're moving at very high velocities. That's what we're trying to show there, which means that gases do not retain either their shape or their volume. A gas will expand to fill the container. And that's what we're saying in this slide. Solids are rigid. They have fixed volume and fixed shape, like ice cubes, diamonds, iron bars. Liquids, they have no specific shape, but they do have a definite volume. such as gasoline, water, alcohol, blood, any of those liquids. This is an example of a liquid acquiring the shape of its container. Gases have no fixed shape and no fixed volume. They will take the shape and the volume of the container. Air is a gas. Actually, air is a mixture of gases. Helium, oxygen. Okay, we're going to talk about properties. Matter can be described as having certain properties. And properties are used to partially identify what the matter is. Right? So a physical property would be, what is its state? Is it a solid, liquid, or gas? Think of properties. We're going to introduce chemical properties as well as physical properties. Think of properties as potential. When we describe a property, it's the potential of that substance to be something or to do something. And they're usually directly observable by some, either with the naked eye, with touch, with our five senses, or with instrumentation. Examples of physical properties: odor, color, volume, the state. Even density is a physical property. Melting point and boiling point. Now, if we have a solid like a cube of ice, we say that its melting point is 0 degrees Celsius. But that doesn't mean it did it. That just means it can do it. If we take that ice up to 0 degrees Celsius, it will melt. It will change its state. But it will not change its identity. It will still be water. Chemical properties, on the other hand, are describing a potential of the substance to convert into some new substance. Right? Some different substance. Its identity will change based upon that property. So examples there are flammability. Right? So you say the sheet of paper is flammable. Now it's not burning yet. Right? It's not changing from cellulose into carbon dioxide, water, but it has that capability. It's the potential. Steel can rust, and steel does rust if it's not protected. Food is digestible. When you eat food, it can provide you with both material, matter, and energy. But that's a chemical property. It describes the ability to change into the different substance. Okay. How about describing physical or chemical properties? Ethyl alcohol boils at 78 degrees. That's physical. Diamond is hard. It's on the Mohs scale, it's the hardest naturally occurring substance at a Mohs scale of 10. Whereas talc is a Mohs scale of 1. Sugar can ferment to form ethyl alcohol. Now, the hardness of diamond is a physical property. Sugar fermenting to form ethyl alcohol, sugar can ferment to form ethyl alcohol, right? Every moonshiner knows that. That's a chemical property. Now, when we talk about change, we're actually describing the transformation of the physical property, the form of the substance. It still retains its identity. So we boil or freeze water. If that actually happens, then you have a physical change. Oh, and by the way, when we write later, when we are going to write words in chemistry, where we combine symbols to make compounds, that we can either say that water is in a gaseous state, it's in the liquid state or it's in the solid state. Right, so the parentheses tell us what the state is. This would be steam, liquid water, and ice. Negative pressure in this room. Okay. A chemical change, on the other hand, describes the change of a substance which involves also changing its identity. In other words, its chemical properties have undergone that change. It becomes a new substance. So when we turn on the Bunsen burner in the laboratory, which unfortunately this doesn't have a lab, when we turn on the burner, natural gas comes through the burner, which is primarily methane, and it's mixed with oxygen from the air, and then we light it, and the chemical change takes place where methane is converted. Methane and oxygen are both together converted into carbon dioxide and water. So that is a chemical change. We produce two new substances with entirely different identities. Or we can, here's an example of electrolysis of water. You can do this. You don't need that fancy outfit. I used to have one of these when I was teaching in high school. And you would electrolyze water, and one of the electrodes, the negative electrode would produce hydrogen gas, positive electrode would produce oxygen gas, and you could open the stopcock at the top and catch the gas in an inverted test tube, and then put your thumb over it, and then have a burning ember or a match, and open it up, put it there, and you go, it would combust. But you can do this yourself if you have a beaker of water and you put a little lemon juice in it or vinegar or even salt, and then you drop a 9-volt battery in it, and you see gases form at the electrodes. The negative electrode will give you the hydrogen gas, and the positive electrode will give you the oxygen gas. This is a decomposition. In other words, we have this molecule. Now we're going to produce hydrogen and oxygen gas. But remember, when I was describing the memorization of some symbols, some of them are diatomic. Right? I described those: hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, iodine. Those are all diatomics. Hydrogen, nitrogen, oxygen, fluorine, iodine. So when you write them, when you see them in a sentence like that, you would write them as diatomics. So that's the decomposition of water. It's just the opposite of the combustion of hydrogen in air, or hydrogen and oxygen in the space shuttle engines. Ideally in the engines. I mean, if you mix them outside the engines and spark them, then you get a disaster. I think that was the Challenger. Okay. So what you're doing is you're supplying enough energy with electricity to break the bonds of the water molecule, and they recombine as elements. All right, chemical changes: pulverizing rock, that's physical. Burning wood, that's a chemical change. Dissolving sugar in water. Did the identity of the sugar change? No. All you have to do is evaporate the water, get the sugar back. Melting a popsicle on a warm day, that's physical change. So the only chemical change is burning wood. Okay. Sugar ferments to alcohol is a chemical change. Iron metal melting is a physical change. Iron combining with oxygen to form rust is a chemical change. in fact, I grew up in Atlanta, Georgia, and we had this place called the Omni. It's where the Atlanta Hawks played their basketball and the Atlanta Flames played their hockey. Well, it was the product of some bright architect's idea to coat the outside of the building with a steel that was specially formulated to rust really fast. The idea was the same as aluminum or stainless steel, that the chrome in stainless steel will oxidize so fast it forms a layer, and then moisture and air can't get to the steel underneath. That's why it stays stainless. Well, his idea was this new steel would rust so fast that it would form a layer on the outside, and the steel underneath would be protected. What he didn't realize was that when rust forms, it has a lower density than the steel underneath. So it expands, and that's why when you see like a tractor or some old car out in the field, it's been there for years, you see layers of steel flaking off in like leaves, because they expand, and that exposes underneath. Well, when it did that, it separated the iron oxide from the surface of the steel just enough so that when it rained, it would slough off. And it sloughed off the building and ran across the concrete, and you have these red streaks all over the concrete. It was ugly. So they eventually tore that building down. I don't know what happened to the architect. He probably had to find a new profession. Okay. So here's the definition of an element. An element is any substance that cannot be broken down into other substances by chemical methods. In other words, you've gone as far as you can go by breaking it down. So water can be broken down into hydrogen and oxygen. You can take bauxite, aluminum oxide, and run it through the Alcoa plant, and it'll come out as aluminum, and the oxygen goes someplace else. But you can do that with any of the elements. Most of the elements in the Earth's crust are combinations. They are compounds. So in order to get them separated, it takes energy. There are a few that are elemental in the ground, like gold flakes, gold nuggets. So examples: iron, Fe. Right? Fe stands for ferrum, which is the Latin for iron. Aluminum, oxygen, hydrogen, those are all elements. All right, a compound is the combination of two or more elements. Now, we mentioned molecule. Molecules can be a combination of any two atoms, and they can be the same element. But compounds have to be two or more different elements. So water would be an example. Table salt, sodium chloride, is a compound. Let's see, glucose that runs through your circulatory system and gives some people trouble is C6H12O6. Right? Table sugar is just actually glucose plus fructose, but it has C12H22O11 is sucrose. Carbon dioxide is CO2. Right, there's table sugar. They have to be different elements to be a compound. Now, they can be molecules also. Like water is a molecule. Sodium chloride is not a molecule because it's composed of separate ions, sodium ions and chloride ions. That's not a representation of the unit that gives it its properties, whereas this is. And hopefully I'll clarify that some point in the future. Compounds, once you've got a pure compound, and pure substances can either be elements, like that's a pure substance, my favorite, gold. Elements are pure substances, but compounds can also be pure substances if there's no other compound or no other element in there with them. So these are all pure substances. And they will have the exact same composition, no matter what the source, no matter where they come from, they will have the same composition, the combination of two hydrogen atoms, or just one gold atom, or two hydrogens, one oxygen, or one sodium, one chlorine. They will always have the same composition. So how many of these are compounds? It looks like all of them are, right? There are different elements in each one. HF, hydrogen fluoride. I used to use concentrated hydrogen fluoride to dissolve soils. It was nasty. Yeah. You get a little drop on you. Funny thing about it, hydrogen fluoride, hydrofluoric acid, we'll just keep eating till it goes all the way through. It won't stop. So I usually wore double gloves on that one. All right. I mentioned pure substances having the same composition throughout. They can be elements or compounds, right? There are various examples. The reason I define pure substance is now I want to talk about mixtures. Mixtures are combinations of pure substances in which the pure substances retain their identities. So salt water, let's use sugar water. Right? You're making a batch of sugar water for your hummingbirds. So you put a cup of water and a cup of hot water and a cup of sugar, and it will dissolve completely. So you make a uniform distribution of sugar throughout that solution. That's a homogeneous mixture. Because no matter where you look in that mixture, you have the same ratio of water to sugar. Now, I can put a lot of sugar or I can just put a little bit of sugar. So the composition is variable, but once it's established, it's the same throughout. Right. That's characteristic of mixtures. They can have variable composition. Let's see. And they can be separated into their pure substances by physical means. So if I want to separate the sugar from the water, all I have to do is evaporate the water, and I got my sugar back. Another name for homogeneous mixture is solution. You can have solutions of various phases. You can mix two solids together and make a solution. It's called an alloy. You have to melt the metals first to get them mixed, but once they've solidified, you have a solution of, say, for brass, it's copper and nickel. Or you can breathe a solution of nitrogen and oxygen and argon and carbon dioxide and water vapor, all those gases, they mix together. And characteristic of mixtures of gases, homogeneous mixtures of gases, you mix two or more gases together, they always form a solution, every time. They never separate on their own because there's lots of room in there. There's plenty of room for everybody. There's airs, brass, I mentioned that one, table salt stirred in water. Heterogeneous mixtures, on the other hand, have visibly distinguishable parts. In other words, their composition, their percent composition is different for different parts of the mixture. You can look at a jar of jelly beans and you'll see different color composition there. And that gives them different properties in their different regions. Heterogeneous mixture, say sand and water. Put the sand in the water and mix it up, and you think you've got a good mixture, and just stop mixing and or vinegar and oil. You're making your own salad dressing. You throw a little Miss Dash in there and you mix it up. If you wait for 30 seconds, you've got separate layers, oil on top and vinegar on the bottom. I have, let's see. I'm not teaching Logan this semester. They didn't have enough students at Southern. But we have this one experiment where I have a mixture of table salt, sodium chloride, and sand, and I know the composition, and I give it to them and say, your experiment is to separate these two. Tell me what the composition is. So you just mix it in water, filter it. It keeps the sand. You dry the paper with the sand in it, get that mass, and then you take the other one with the salt water that went through the filter and evaporate the water, and you got your salt. So you compare the two masses and you get a composition. All right. Which of the following is homogeneous mixture? Well, this is the type of question that I like to work backwards. Which one is a mixture? Water's not a mixture. Copper metal's not a mixture. Those are pure substances. So we're left with gasoline, jelly beans, and soil. So which of these is homogeneous? Gasoline, definitely. That's octane and a bunch of additives, up to 10% ethanol, I think, and then some other things. Jelly beans is heterogeneous. We know that. And take my word for it, soil is heterogeneous too. I mean, I spent several years working on a PhD in soil, so definitely they're heterogeneous. Okay. The one thing about the physical properties of a substance allows you to separate mixtures into their pure substances. If you have a boiling point difference in your mixture, then you can distill them. Like water and ethanol boil at different temperatures. So every moonshiner knows that once his mash is ready, he just shoves the burner under the can and evaporates the alcohol. And it goes across, it runs through, let's see, it runs through a coil first and goes through a thumper and then out to the spigot. And then he collects the first fraction, which is methanol, and throws that out because that's wood alcohol and it'll make you go blind. And then he catches the ethanol. He or she, I guess you could have female moonshiners. Yeah. That's distillation. You can separate the ethanol from the mash for distillation. It's a physical process. The states of matter, if you have a solid, liquid, or gas, sometimes filtration will work, especially if you have a solid and a liquid, and the solid is not soluble in the liquid, then filtration will take advantage of that. If you know that the substances in your mixture have a variable attraction to a stationary substance like a paper strip, you can put the mixture on the paper strip and let it dry, and then dip the tip of it in some solvent like ethanol or acetone or something, and then put it in a jar and close the lid. And you watch the liquid migrate up the paper. And gradually, the substances in that line that you drew there will separate. That's because some substances in that paper, like we start here, some are strongly attached to the paper and they don't dissolve well in the solvent. So as the solvent moves up, they only move a little bit. But some are very soluble in the mobile phase, we call it, and they're not attracted too strongly to the paper, and they move faster. So we use that variable attraction to the paper in order to separate them. And in fact, that was the first chromatography, was extracts of leaves on paper. Volatility. Well, if something's more volatile than another one, all you have to do is evaporate it. That's kind of a variation on distillation, I think. All right. So I'm not going to dwell on this. This is a setup for distillation. You can remove water from salt water, and this is how large volumes of potable water are made from salt water distillation. That's one way. There's another way, but it takes a little more time to explain. Okay, no chemical changes were noted, right? You started off with water and salt mixed, you ended up with water and salt separate. Their identities did not change. Filtration is another possibility. Organization of matter, okay. You can have mixtures, homogeneous or heterogeneous. You can separate them by physical methods. Or if the matter is a pure substance, you just work your way down to the pure substance and skips the mixtures. But you can only separate pure substances into elements by chemical means. All right, we're done.